This video is on functions, injections, and surjections. A function mapping a set x to a set y is a rule that assigns a unique y in y to each x in x. And in mathematics, remember, unique means different or distinct. Y1 not equal to y2. So just to think about this definition, are the following rules functions? So let's look at first f of x equals the square root of x, mapping the real numbers to the real numbers. And then next, let's look at these three rules. And we have these different rules mapping the set A, B, C into the real numbers. For example, h of A is 1, h of B is 3, and h of C is 3, for example. So are any of those three functions, and if so, which ones? So I would like you to pause and think about that, and we'll talk about it in a moment. Okay, so f of x is square root of x, mapping the real numbers to the real numbers. So here on the side is just our definition written in shorthand mathematics. So again, f of x, f mapping x to y is a function if for every x in the set x, there is a unique, that exclamation point means unique, there is a unique y in y such that f of x equals y. So is that true in this case? This is not a function, potentially for two reasons, depending on how you interpret this square root. One issue is if this is like the positive or negative square root. So for example, the square root of 9, depending on how you're interpreting it, that might be interpreted as positive or negative 3, in which case there is not a unique y in y such that f of x equals y. So since f of 9 is equal to both 3 and negative 3, the output is not unique for this input, and that would make this not a function. Secondly, it needs to be the case that for every x in x, f of x needs to be defined. And here we see that something like f of negative 4 is not defined, does not exist, because f is mapping the real numbers to the real numbers. F of negative 4, we could say it's 2 times the square root of negative 1. We could say it's 2i, but since that's not a real number, that output is not defined. So there are two reasons here why this function, f of x, is not a function. If we edited it, we could edit that function to be like, say, g mapping the interval from 0 to infinity to the real numbers by, let's say, g of x is equal to the absolute value of the square root of x. In that case, g would, in fact, be a function. Okay, how about these other three rules, h, g, and t, mapping the set A, B, C to the set of real numbers? So let's look first at kind of the most straightforward looking one, g. So g of A is equal to 1, g of B is equal to 2, and g of C is equal to 3. So that tells us that, yes, for every element of this set, there is one unique output. And so, yes, this is a function. How about h of x? So h of A is 1, h of B is 3, h of C is 3. So for the element A, there is a unique output. For the element B, there is a unique output. For the element C, there is a unique output. So yes, this is a function. It can be the case that two different elements map to the same element. That is okay. It has to be that for the x, for this given x in x, there is a unique output for that value of x. And that is satisfied by h of x. How about t of x? So here we have an issue. Here we have t of A is both 1 and 3, so this would be no, there's not any unique output for A. So h of x is a function, g of x is a function, t of x is not a function. A function f mapping x to y is injective, or 1-to-1, if for all a and b in x, f of a equals f of b implies a equals b. So to kind of unwrap that, what we're saying is that if we've got two sets and we have a function mapping over it, then if it's the case that f of a is actually equal to f of b, if they are actually the same point, then this point over here, a and b must have been the same point. That's what that is saying above. We could also state this in the contrapositive of this form. So that would be saying that a not equal to b implies that f of a is not equal to f of b. That would be the contrapositive, which is a logically equivalent statement. So in other words, if it's the case, let's just try it again, if it's the case that a is not equal to the point b, then it must also be the case that f of a is not equal to the point f of b. So basically, one-to-one, this is also called one-to-one because sort of for every one thing over here, we've got one thing over there. For every one thing over here, we've got one thing over there, and so on. So that's one-to-one. It's stated in both ways. This can be the sort of easier way of proving it. So to prove one-to-one or injective, we often want to say, okay, suppose that a and b are in X. Suppose f of a equals f of b. We want to show that means that a must equal b. Okay, one final way to say this is to say that distinct inputs must have distinct outputs. So distinct inputs must have distinct or different outputs. So that's just another way to say what it means to be one-to-one. All right, so here are a couple examples. Are the following functions injective? In either case, fully justify your answer. So our first function is the function f of x is x squared, mapping the real numbers to the real numbers. The second is f of x equals 2x plus 4, mapping the real numbers to the real numbers. All right, so f of x equals x squared. We could start by sort of thinking of this as the function that it is, as drawing it sloppily. You may have also seen that being one-to-one is equivalent to passing the horizontal line test. So here we see that this is not passing the horizontal line test. So for example, f of 1 is the same thing as f of negative 1. And this is okay, it's still a function, but it is not going to be an injective function because it's the case that f of negative 1 is equal to f of 1, but 1 is not equal to negative 1. So we are not following the rule above that if f of negative 1 equals f of 1, it must be the case that 1 is equal to negative 1. If the outputs are equal, it must be the case that the inputs were equal. So no, this is not injective. How about f of x equals 2x plus 4? We could start by sort of drawing it, and it's a line, 2x plus 4. Cool. So it's a line. And we can see that, if we think about any horizontal line, it's going to pass the horizontal line test. That's not, however, a proof for a full justification, at least in terms of this course. We want to be able to use this definition to prove that this is an injective function. So we're going to suppose it's the case that f of a is equal to f of b for some real numbers, a and b in the real numbers. And we want to show that that means that a is equal to b. So let's try to do that. Since f of a is equal to f of b, that then implies that 2a plus 4 is equal to 2b plus 4. That's the definition of this function. And so therefore, we could subtract 4 from both sides. 2a equals 2b, and therefore a is equal to b. So we have shown that if the outputs are equal, then the inputs must be equal, and therefore this is a one-to-one function. So yes, this is injective or one-to-one. A function f mapping x to y is surjective or onto. if f of x is equal to y, that is, for any y in the codomain, there is some x in x such that f of x is equal to y. So a picture to kind of go with this f mapping a set x to a set y is that everything is actually covered in x. So this would be a function that is onto, whereas a function that is not onto, maybe you could like draw in such a way. So f mapping a set x to a set y would not be onto if the range of the function was less than the entire codomain. So again, we're trying to show for any y in y, there exists some x in x such that f of x equals y. For any y in the codomain, there's some x in the domain that maps onto it. So let's look at these examples. Are the following functions surjective? Whether they are or are not, fully justify your answer. So 1, f of x is x squared, f mapping the real numbers to the real numbers. 2, f of x is 2x plus 4, again, f mapping the real numbers to the reals. And finally, g of x is 2x plus 4, where g maps the integers to the integers. So pause and try those out. We'll talk about them in a moment. All right, so is this a surjective function? Again, thinking about this function, what is the range of this function compared to the codomain? So the codomain is all of R, but the range of this function is only, it only maps to the set 0 to infinity is the range of this function. So this is not surjective or not onto, and it's not surjective because, for example, -1 is an element of R, but there is no x in the real numbers such that f of x is equal to -1. So this is not a surjective function. We could edit this function to make it surjective. So for example, h of x equals x squared, where h maps the real numbers to the set 0, infinity. That would be surjective. So that can be edited to become a surjective function. All right, how about f of x equals 2x plus 4? F maps the real numbers to the real numbers. Again, if we're thinking about drawing this function, we can kind of see that, every y value is going to be the output of some x value. So to prove that that's the case, let's let y be in the real numbers, and let's try to find some x that gets us there. So if f of x is equal to y, then that means that 2x plus 4 is equal to y. So we could subtract, and we've got 2x is equal to y minus 4, and that tells us that x is equal to y over 2 minus 4 over 2 minus 2. And since y is a real number, that would be in the real numbers as well. So that tells us that, yes, for y in the real numbers, there is this x in the real numbers, y over 2 minus 2 in the reals, such that f of y over 2 minus 2 is equal to y. So yes, this is a surjective function. All right, what if we just change this function slightly by changing its domain and range, or its domain and codomain? So now, again, we can sort of look at the same kind of thing. If y is equal to g of x, as we saw above, that would mean that y is equal to 2x plus 4. And so, again, as we saw, that means that x would be equal to y over 2 minus 2 when we solve for x. Is this always going to be in the domain? So is that always in this domain? Not necessarily, right? So for example, what if y was 3? So let's say 3 is an element of the integers. Then this is not going to be an integer. So y is in the integers. Y3 is equal to 2x plus 4. Subtracting over, we've got negative 1 equals 2x, and that means negative 1/2 is equal to x. Only x equals negative 1/2 could map to it, and this is not in the integers. So there is no x in the domain such that g of x equals 3, but 3 is in the codomain. So this is not surjective. If a function is both injective and surjective, then it is called a bijection, or is bijective. It's also called a one-to-one correspondence between the sets x and y. So in that case, if it's a bijection, both for every y there is a unique x, for every x there is a unique y. So everything in the codomain gets hit. The codomain is equal to the range, and there's never a case where two x values map to the same y value. So for example, as we saw above, let's say f of x equals 2x plus 4 is a one-to-one correspondence, or is a bijective function. But most of our other examples, or this is where f mapped the real numbers to the real numbers, that was a one-to-one correspondence, whereas say f of x equals x squared was not a one-to-one correspondence, is not a bijection.